Alright, this is the notes today for 6-2. What we want to do today is we want to look at the relationship between absolute value and square roots, and then relate it to the idea of how we can use it to solve quadratic equations. So first of all, when we talk about absolute value, our first definition of absolute value is really more of a geometric definition, and that is that n can be described as the distance from zero on a number line. But as soon as we go to two dimensions, we want to look at it more from the standpoint of algebraically, how can we define it? And algebraically, we can define it really as a piecewise linear function. So what we can say is that the absolute value of x, is how we write that, remember? It's always going to be equal to x if x is greater than or equal to 0. But it's going to be equal to the opposite of x when x is less than 0. Notice how I'm saying opposite of x instead of negative x, because the opposite of x could be a positive number. Okay, so that's what we mean by absolute value. Now graphically, this is what that would look like right over here. Okay, so you'll notice that when it hits 0, it pops back up. So it's the line y equals x when x is greater than 0, and y equals negative x when x is less than 0. Alright, so in this first example problem, what I'd like to do is I'd like to first look at the graph to show you that there are actually two solutions to this. So if I graph y equals f of x, or excuse me, f of x equals x plus 6 and f of x equals 7.2, you'll notice that when I do that, I'm just doing it on decimals, there's actually two intersection points. So there is two solutions to that problem, and it all goes back to this idea of a piecewise linear function. We know it's equal to x when x is greater than or equal to 0, and negative x here. So really what we're saying is this. We're saying that in order for us to solve this problem, what we're going to do is we're going to say x plus 6 is equal to 7.2, or x plus 6 is equal to negative 7.2. And by doing that, and really we're just using this to help us do that, now we can solve both of these and get our two solutions. So if I subtract 6 from both sides here, we have x is equal to 1.2. And if I subtract 6 from both sides over here, I have x is equal to negative 13.2. So our two solutions are x equals 1.2 and x equals negative 13.2. And let's show that that's the case on the graph over here. There's 1 point, and here's our second point, 1.2 and negative 13.2. Alright, next what I'd like to do is examine the relationship between the absolute value of x and the square root of x. What I've done is I've taken, I'm just calling my variable x of 1, and I've listed several different values of x of 1. And then I took the absolute value of it and got those values, and I have those values plotted over here. And then I did the same thing with x squared, and you'll notice that those values for the square root of x squared are exactly the same as the absolute value of x. And if I plot those values, you'll notice that those ended up in the exact same spot. Now if we actually graph the functions, here's the function of f of x equals the absolute value of x, and here's the function for g of x, which is the square root of x squared. Notice how they're exactly the same. Now this leads to the absolute value square root theorem, which just says that for all real numbers x, the square root of x squared will always be equal to the absolute value of x. Alright, this relationship between absolute value and square root is what allows us to do what we've been doing for a long time, which is this right here, and that is if x squared is equal to some number k, okay, where k is greater than 0, so k is positive, then the square root of k will be equal to the square root of k and the opposite of the square root of k. So when we take the square root of a number, we are getting both the positive and negative values of that. We've been doing that for a long time, but really it's the relationship between absolute value and square root that allows us to do that. All right, so let's apply these concepts involving absolute value and square roots to solve a quadratic equation. So if I'm going to solve this right here is a quadratic because we have a squared as our highest power there. I'm going to start by doing what I would always do, and that's just divide by 3 on both sides. Therefore, x squared would be equal to 40. And now, if I'm going to get rid of the square, I'm going to take the square root of both sides. Well, we know the square root of x squared is really going to be two separate things. We have x is going to be equal to the square root of 40, and x is going to be equal to the opposite of that, or negative square root of 40. So we actually have two answers. X can be this or this. So this would be the solution to that quadratic. So let's take a look at this third example, and it says the following. An equilateral triangle and a circle have the same area. The triangle has side lengths of 20 centimeters. Which is greater, the side length of a triangle or the diameter of the circle? Well, if they have the same area, the first thing that I want to do is, I've drawn a triangle here, is that I want to find the area of that triangle. So I need to use a little bit of geometry to do that. We know that the area of a triangle is equal to 1/2 its base times its height. So the base would be this total distance going across here, or really we could do any side, but we know that's 20. Okay? But the height we aren't quite sure about, so we have to call up on some geometry from last year, and we know that it's an equilateral triangle, therefore this angle is 60 degrees, and this angle then, if it's cut in half, would have to be 30 degrees. It's a 30, 60, 90, and we learned last year that if it's a 30, 60, 90 degree triangle, then this side would be, this distance from A to D here would have to be 10, half of it, and that means this height would have to be 10 times the square root of 3. So thinking of our special right triangles from last year. So if the height is 10 square root of 3 and the base is 20, the area of my triangle is equal to 1/2 times the base of 20 times the height of 10 square root of 3. Now what I'm going to do is I'm going to simplify that, but I'm going to leave it as an exact value. So 1/2 times 20 is 10. 10 times 10 is 100. So we can think of this as being the area is equal to 100 times the square root of 3. Now, I also know from geometry last year that the area of a circle is equal to pi r squared. And we also know the relationship because in the end we want to know diameter. We know that the diameter is equal to 2 times the radius. So if I can solve for the radius, I can find the diameter. Alright, so since the area of the circle and the triangle are the same, I can substitute in 100 times the square root of 3 for the area. I've got pi here, and I've got the radius squared. So now what I'm going to do is I'm going to solve for the radius. So I'm going to divide both sides by pi. So I have 100 over the square root of 3 divided by pi is equal to the radius squared. And what I'm going to do to finish that off is take the square root of both sides. Okay. So on my calculator I can get an approximation for that radius. So if we want it, you can just plug this right into your calculator to get that. So if we do that, we get about 7.43 approximately for the radius. Now remember, it could be plus or minus that. Okay. However, we're not really interested in the minus aspect of it because we're talking about real life situation. We know that in reality the radius can only be a positive value, can't be a negative value. Okay? Which leads us one more step, and that is to use this radius to find its diameter. So let's do that. So I'm going to take this radius and plug it in up here. So the diameter is equal to, or approximately equal to, 2 times 7.43, which is about about 14.86. So the approximate diameter is 14.86, which is definitely less than 20, which is the length of the triangle. Therefore, the answer is to this question is the side length of the triangle is longer. All right, the final thing I'd like to look at is a concept that you should be familiar with already, and that's the idea of rational numbers and irrational numbers. Really, the key to rational and irrational numbers is, can the number be written as a fraction? So any number that can be written as a fraction, a over b, is considered a rational number. An irrational number is not rational, so everything that is not rational would be irrational, and cannot be expressed as a simple fraction, a over b. So when we think about irrational numbers, generally we're thinking about special numbers like pi, or as we'll learn a little bit later, e, and also square roots of numbers that are not perfect squares. So in both examples 2 and 3, we use some irrational numbers. My final answer in 3 wasn't irrational. I did some rounding there, but my final answer in 2 was an irrational number.